You're welcome. In this short video, we're going to talk about angle bisectors. We're going to talk about the angle bisector as the locus of points equidistant to two given lines. So let's look at this triangle ABC. Now, why are we talking about angle bisectors? We're talking about constructing the incenter of the circle. So the incenter of the circle is the center of the inscribed circle, which best matches the triangle there. And the incenter is located at the point of intersection of the three angle bisectors that bisect angles A, B, and C. So if we draw the angle bisectors and find where they intersect, then we'll have located the incenter of the circle. Now, I want to demonstrate that the angle bisector is the locus of points which are equidistant to the two lines. So what we're going to do is we're going to focus all of our attention here on the angle C and the angle bisector of C. So I want you to sort of ignore most of the triangle and focus your attention only on the angle C together with its angle bisector. Now, this angle bisector, let me draw it a little bit more precisely so that we can really have a close look at it. It looks like it's about here, so I'm just going to eyeball it instead of literally geometrically constructing it, but I want it to be pretty decent. So that's pretty bad. So that's a little bit more precise. So that looks like the angle bisector of the angle C here. Now, if we take any point on the angle bisector here, then we can drop two perpendiculars, one to each line. And the reason I'm dropping these is because they will calculate the distance from that point to the various edges, that is the two lines here. So we can drop two different perpendiculars. Now this angle is pretty sharp here, and so these are close to being on the same line, but these of course don't lie on the same line, right? This one is perpendicular to this edge, and this one is perpendicular to that edge. Now, if we get this diagram in place, then we can identify two triangles here, right? Let's call this D, let's call this E, and let's call this point here F. So we have two right triangles because the angles at E and at F are right angles. What can we do with this? Well, we actually have quite a bit of information about the angles. If these are angle bisectors, so if CF bisects angle DCE, then the one thing we know about these angles is that this one has to match that one. So angle DCF equals angle FCE here. Those two angles are equal. And certainly, we have angle E equals angle D because they're right angles. And so that gives us an angle equality and another angle equality. Do we have any more feature equalities in these triangles? Well, certainly, because we have CF, which is shared between the triangles. So CF equals CF. And that gives us one side and an angle and another angle. And so by the angle-side congruence criterion, we have triangle. And now I want to remind you that whenever we name a triangle congruence, we need to be careful to name it in the appropriate order. It is so if we say CDF is our name for this triangle, then we must carefully give corresponding vertices in the right and corresponding order for the statement of the other triangle. I can't say CFE. So this is congruent to triangle CEF. Notice it has to be this way because angle D matches angle E. And so they should both appear second here. And for example, length CF matches length CF here. And so, etc. So that's the correct order in which to name the congruence of these triangles. If we get the congruence of the triangles, then what's the point? Then we know that FD is equal to FE. That's because corresponding parts of congruent triangles are congruent, which can either be called the definition of congruence or it can be called CP/CTC, depending on how you like to work. But whenever we have triangles that are congruent, then corresponding features of them are equal. So this means, so let me interpret this. So F is equidistant from line CE and line CD. And now I'm saying line CD, I really mean the entire line, not the segment, right? The distance between F and the line, the original line here, is going to be equal. F is equidistant from this line as this line. And you might think that, you know, all of the points that are equidistant will also lie on this ray, right? You might think if you can pick any other point equidistant to these two lines, then it must lie on the angle bisector. It must lie on this ray. But we have to be careful here. That's not the only, those aren't all of the points that are equidistant to the two lines, because there are more such points over here. But what's a little harder to spot in this picture is that there are more such points up here bisecting the other angle made by these two lines, right? So these two lines make this angle and this angle. These are called vertical angles here. We bisect them both with the same line, but they also make this large angle here and this large angle here, and those two are bisected with this line. And so those points are, for the same reason, equidistant from the two lines. So if we restore our picture to include, or approximately restore our picture, I won't get it exactly the same. If we restore our picture to include the rest of the original triangle, so that we have the point B again, and then we have the point A, and then we have not one angle bisector, but three of them in this picture. So then I have an angle bisector here, and I have an angle bisector here, and they all come together and meet at the incenter, which I'll call I. So in the context of having the complete triangle here, so what do we know about I? On the grounds that I is on this original bisector, I is equidistant to lines BC and AC, right? This line and that line. The distance from I to those lines is equal in both cases. And let's draw it in pink as a perpendicular. So this thing is equal to this thing. But moreover, if I is also on this angle bisector, bisecting angle A, then I is going to be equidistant to the lines AC and AB, which tells us that we have an equality between the perpendiculars here and here. That is the perpendicular distance from I to this and from I to that. But you can see here that the pink thing I drew, dropping a perpendicular from I to line AC, and the blue thing that I drew, doing exactly the same thing, those are the same length. And so I'm illustrating two colors to illustrate that there are two possible principles involved. But the fact is, we've got three different lengths and they're all equal, right? These two are equal for this reason, and these two are equal for this reason, and so all three are equal, which means I'm not really justified using two different colors. So let me replace this with pink. So this is fundamentally the reason why the incircle with this radius, with this pink radius, all of these pink lengths being equal, this is the fundamental reason why that circle with that radius meets the triangle so successfully, tangentially that is, at these 3 points. It's because these 3 pink edges are 3 of the radii of that incircle, and they are perpendicular to the 3 lines defining the triangle, and so they will be tangent. So the circle with that radius will be tangent to the triangle. So this shows how we can produce a circle which is equidistant to the 3 lines, and that's kind of interesting, to be able to construct a circle equidistant to the 3 lines. But it is not the only way to draw a circle equidistant to the 3 lines of the triangle. And you might say to yourself, wait a minute, how can we have another triangle? How can we have another circle inside the triangle that meets all of its lines so perfectly? And the answer is, well, we can't have another circle inside the triangle whose center is equidistant to all of the lines of the triangle, but we can get one on the outside. And let me illustrate that next. So it's going to be easier to illustrate it over here. These angles defining the triangle also have exterior bisectors. And if instead of using the interior bisectors, we use the exterior bisectors, then we will again get locuses of points which are equidistant to those lines. So this red bisector bisecting the exterior angle B is a locus of points equidistant to line AB and, well, technically line BC, right? Because this is still line BC. So any point along this red locus is equidistant to these two extended lines, namely AB and line BC. So we have a locus of points equidistant. Now, the interior angle for C the interior bisector for C can be continued out here, and it still represents a locus of points equidistant from line BC and line AC. Notice the reuse of the line BC here. And so if we simply take the point of intersection of those two, now that's obviously not the incenter, but it must be something, because these points here, for reasons which will be expressed in red, are equidistant. So we're going to call this point IC, just so we can refer to it. We'll call that I sub C. Such a point is equidistant from the lines AB and BC. Let me write that in red. So I sub C is equidistant to lines AB and BC. But if we think of this as being another reason, we can also see that that point of intersection is equidistant to lines AC and BC, because on the grounds that IC is on this angle bisector as well, it's equidistant from these two lines. And so when I calculate its distance to this line and its distance to this line, I get the same thing. And here again we have the same argument. In red, I've recorded the fact that it's equidistant to these two lines. In blue, I've recorded the fact that it's equidistant to these two lines. But that means that these two lengths are equal and these two lengths are equal, and so all three of these lengths are equal, which means I'm not really justified giving it two different colors. And I'm going to do the same thing again that I did before. In this case, I'll just color everything blue. So these three blue lengths are equal. And that means that a circle can be drawn with that as its center. Now, this circle, which is, okay, I admit, a little lopsided, but if we trust the geometry, so these are appearing slightly different in length. So if I really want to get it perfect, I labeled IC a little bit too close, but bear with me. So when we draw a circle here, whose radius is this blue length, because it has these three equal lengths, this circle is likewise, just like that one, is tangent to the three lines defining the triangle. Now, it's the extended edges of the triangle, but they're still the same lines. So notice that it's drawn, I called it IC because it is, in a sense, across from C. So this is the notion of the excircle. This is the incircle, inside. We call this an excircle. It is outside, right? X means outside, or out from. So X means it's outside. This is just like the incircle, but outside. It has a lot in common with the incircle. In particular, it is centered at a point which is equidistant from the three extended edges of the triangle. So many of the things that we can calculate for incircles, we can also calculate for excircles. Is there just one? Does every triangle have just one excircle? No. Every triangle has 3 excircles. One of them across from C in the way that I've drawn. One of them across from A. It would be huge out here. And one of them across from B, which would be, in my diagram, it would be enormous, and it would be centered way down below the whiteboard. So we have these 3 excircles for any triangle. And once we sketch them all, then we have the glorious opportunity to connect their centers and make another exterior triangle. And we'll read more about that in our textbook.